Okay, we have another block spring problem on an incline. So a block of mass, 12 kilograms, is released from rest on a frictionless incline of angle 30 degrees. Below the block is a spring that can be compressed 2 centimeters by a force of 270 newtons. The block momentarily stops when it compresses the spring by 5.5 centimeters. A. How far does the block move down the incline from its rest position to this stopping point? B. What is the speed of the block just as it touches the spring? Well, the first thing we're going to have to do is get the spring constant. So we're going to use Hooke's law for that. And Hooke's law is force is equal to minus the spring constant times the distance that the spring is compressed. So that would go to K, and we're not going to use the negative sign. The negative sign just indicates that when you pull the spring, it pulls back in the opposite direction. So it's equal to force divided by X. So that is Newton. The units will be newtons meters for the spring constant. So in this case, we have K is equal to, they gave us 270 newtons when it's compressed, 270 newtons divided by 0.02 meters. And when you do the math on that, that comes out to be 13,500 Newton meters. So now that we know that, we want to figure out the distance L when this block between the spring before it's compressed and the block. So let's figure out what the distance is when the spring is fully compressed, and then just subtract the 5.5 centimeters from it, and that should give us our energy in this system. And we know the potential energy, U, is equal to 1/2 K X squared. Now this is the compression of the spring. So what we have here is 1/2 times 13,500, and that's in Newton meters, times the compression of the spring squared. So that is, we see the spring goes up 5.5 centimeters, so that's 0.055 meters. Squared. And when you do the math on that, that should equal 20 0.4 joules. Now that we have how much energy is available, let's go to our potential energy formula, which will be, in this case, mg, this is usually h, for the height, is equal to, 20.4 joules. So let's just solve for the height of this block. We're solving, we got this block still. We got the wedge, we have the block on it. We have the spring down here. We have this distance L, we just call it L prime, and then we got from here to here, which is when it's compressed. So we'll solve for H, and that's going to be this H is going to equal 20.4 joules divided by 9.8, that's G, times M, the mass, and the mass is given to us as 12 kg. So with this, we know that the height of this block, h, when we do the math on this, is going to equal 0.173 meters. All right, now we want to find L. This would be the L compressed. So let's do that. Let's say the sine. Now we have here, this is 30 degrees. The sine 30 degrees is equal to this side, which h is equal to h, which is 0.173 over this compressed L that we're looking for. So we'll just solve for L. So L, let's go to, is going to equal to 0.173 divided by the sine of 30 degrees, which is 0.5. So we have L, just bring it over here, is going to equal 0.346 meters. That's the L when the spring is compressed. So L from when the block comes from this point to this point will just be the 5.5 centimeters subtracted from this 0.346 meters. So we'll just say L, we'll just put prime there. You know what I mean. This L here, with the non-compressed that they're asking for, which is going to be simply 0.346 minus 0.055, and that's going to equal 0.291 meters. Okay. So that's what the L that we're looking for. And that's the answer to the first part, A. So part A, we have L equal to 0.291 meters. Now B, it says, what is the speed of the block just as it touches the spring? Well, that's this, we need this L here, which we can compute it for that. So let's just go back. And I'm going to use a kinematic to work this problem. We know that this block on this incline moves in this direction with a force of mg sine theta. That's the force. We also know that the mass of the block that was given as 12 kilograms. So force is equal to mass times acceleration. So this will go to acceleration is equal to the force divided by the mass, which is going to equal mg sine theta over m. Masses will cancel, so acceleration is just going to equal g sine theta. Well, we know theta is 30 degrees, so this would be equal 9.8 times 0.5, which would be equal to is 4.9 meters per second square. So we have the acceleration of this block, and we want to know the just before this block touches this spring, we want to know what is the velocity at this point, just before it touches the spring. So we know that v squared final is equal to v squared initial plus 2 times the acceleration times the change in position, which is going to be L in this case. So let's just solve for it. So V found is going to equal the square root. V initial, well, that's 0, plus 2 times 4.9, that takes that right back to 9.8, times, well, L. And now L happened to be, put it here somewhere, zero point 291 meters. And when you finish doing this math, V will equal 1.68 meters per second. That's the answer. For V, the velocity just before it hit the spring. So just to summarize real quick, we took Hooke's law, came up with the spring constant. We used the potential energy formula to come up with how much energy we had in the system. And then we took that, knowing that we had 20.4 joules of energy, we set it to the potential energy and solved for H. We needed H so we could find this L, compressed L, because that's this came from compressing the spring. So when we solve for H, we got 0.173. We just use a trig formula to find L. And once we found L, that's the compressed L, we subtracted the spring, the length of the spring from it, and we came up with the 0.291, which is the L non-compressed. Then we said, well, let's make it easier on ourselves. We knew that the acceleration is force over mass, so we solved for the acceleration of this system, just moving freely down this friction, no friction on this ramp. So moving freely down the ramp, and we said, wow, since we got a constant acceleration, this is ideal for a kinematic formula. So we set it in our kinematic formula, and what we came up with 1.68 meters per second for the velocity just before it touched the spring. So that's it for this problem.